Morning, everyone. Thank you for coming to my webinar. My name is Jian Yang. I'm an assistant professor at the Delft University of Technology. So today I'm going to talk about engineering porous materials for broadband sound absorption from Metaporous layers to 3D printed lattice structures. Before begin, I would like to introduce myself. Again, my name is Jian Yang. I'm an assistant professor at the Department of Precision and Microsystems Engineering within the Faculty of Mechanical Engineering at Delft University of Technology in the Netherlands. I am originally from South Korea. I studied mechanical engineering for my bachelor and PhD degrees at Seoul National University. And after that, I worked at Samsung Electronics for like 2.5 years. Then after that, I moved to the Netherlands and I started working as a postdoc and later then assistant professor at Eindhoven University of Technology. Then after that, I moved to TU Delft and started working there from July last year. And my research interests include metamaterials and architected materials to control wave dynamics, mostly focused on noise and vibration reduction. But I'm also expanding my research interest into multifunctional materials. And then my usual application area of interest is in high-tech industry, manufacturing, or maritime or aerospace industries. So today's presentation, so I'm going to talk these three works of mine. Two of them are about Metaporous layers, which I worked on during my PhD study, and also a relatively new one, 3D printed lattice structure that I worked together with my PhD student. So I first would like to introduce about acoustic porous materials. So porous materials are widely used in many applications to reduce sound and also noise. They have pore structures, and then by the viscous and thermal dissipation of waves going through them, they can reduce acoustic energies. And their performance are usually dependent on the thickness of the layer. So when you increase the thickness, their overall performance are getting better, and also the broadband performance as well. So my work was usually focused on improving the broadband sound absorption performance of such porous layer while maintaining the thickness of the layer. So I first would like to start with my first work that I conducted during my PhD, which is about Metaporous layer with tuned thickness resonances. And in this work, I put some rigid partitions on the vertical ways to manipulate wave propagation inside the layer. And then I will explain more details in the following slide. So I first want to mention sound absorption properties of a finite thickness porous layer. So when we have this finite thickness porous layer, the sound absorption performance of such a layer looks like this graph on the right-hand side. Then you see that there are small absorption peaks and small troughs on this area. And then these frequencies are usually determined by the relationship between the thickness of the layer and also the wavelengths. So when the thickness of the layer is odd multiple of the quarter wavelengths, then you have slightly higher absorption. And when the thickness of the layer coincides the even multiple of quarter wavelengths, then you have slightly lower sound absorption. And then we called it as a thickness resonances. And if you put thin rigid partitions periodically in the porous layer, then you see that there is a very slight increase on this absorption peak and also a small decrease on these draws. And if we increase the thickness of these rigid partitions, then you see that there is a little bit increase on these absorption peaks. And if we further increase the thickness of these partitions, then you see that there are almost full absorptions on these absorption peaks. And then we wanted to understand why that was happening. So we decided to model this porous layer with rigid partitions as homogeneous effective anisotropic medium. So when the size of the unit cell is smaller than the wavelength, then this periodic layer can be regarded as a homogeneous effective layer. And we can model by considering the effective density and bulk modulus of porous material, and also rigid material that's like infinity value. Then we can get the effective density and effective bulk modulus, which is determined by the volume fraction of porous material in a unit cell, this eta. Then we can calculate the effective surface impedance by using this effective density and bulk modulus, and then calculate reflection coefficient and absorption coefficient from this. So we calculate this absorption coefficient by using this theoretical model, and also conducted a finite elements method simulation to compare the result. And then we see that there is a very good match between the theoretical model and also numerical simulation. And then why do we actually get this high peak when we put these rigid partitions in the porous layer? Then if we check the effective surface impedance, and then I have this graph of real part of the impedance and the imaginary part of the impedance here. And at these absorption peaks, the imaginary part of the effective surface impedance are 0. And there are certain values for the real part. But if we put these rigid partitions, and then the real part of the surface impedance increases, and they actually get closer to the characteristic impedance of the air. So if you put these rigid partitions, actually the impedance between the characteristic impedance of the air and the surface impedance of this layer got matched. So they lead to the increase of the absorption coefficient at these corresponding frequencies. Yeah, and then this is what we got for the 3 centimeter porous layer with rigid partitions. But yeah, you can see that there are increase on this absorption peak, but there are also decrease in the other frequency ranges. So we wanted to improve the other frequency range as well. Then we thought that maybe if we can change the thickness and then combine these 2 layers into one, then we can have more broadband improvement of sound absorption. So we designed this type of layer, which is connected to connected unit cell of 2 different thicknesses. And then by the combined effect of this 3 centimeter thickness and also a 2 centimeter thickness, you can get several peaks combined in one layer. And then we also made a theoretical model for this combined layer by using the parallel combination of surface impedances. Also compare the result with a finite element simulation. But you also see that while we improved sound absorption on this frequency range, but we couldn't actually improve the absorption performance at frequencies below the first peak frequency. So we were thinking how to improve that frequency range, and then this was the final design we thought of. So we made small hole so the acoustic wave can go through to this side, so that the effective propagation lengths of the waves are longer than the actual thickness of the layer. And then by the combined effect of impedance matching and also wave propagation, path elongation, and also multiple thickness resonances, yeah, we could get the improvement of sound absorption in a wider frequency range, including the low frequency range. And we wanted to make also theoretical model of this new subcell. And then this was the model that we made at the time. It is actually quite similar to coiling of space that is widely used for metamaterial design, but we had this quite small gap. So we thought just using that wave elongation path was not really fitting to our design. So we combined the surface impedance of Helmholtz resonator here. But in the end, this equation is mostly governed by the surface impedance of the elongated path. And these are the also the comparison between theoretical model and finite element simulation. And then you can see that the first peak of this sound absorbing layer gets shifted to lower frequency by having this elongated path. So by using this principle, we could also design several other unicell designs to have more broadband sound absorption improvement of this porous layer. And we could also say that in this first work, we changed the effective thickness of the porous layers by inserting those rigid partitions, and then changed the location of the thickness resonances. But for this design, we also calculate this effective acoustic density and bulk modulus. But in the end, the effective wave propagation velocity inside this homogeneous effective anisotropic medium was the same as the original wave velocity in homogeneous porous medium. If you see the thickness resonance condition, this equation, then we can also see that we can change the frequency, the absorption peak frequency by contouring the thickness, but also by contouring the wave velocity inside the porous layer. So my second work was about changing the sound propagation velocity inside the porous layer. But to tell you the background story, we were not actually thinking about changing the velocity inside the porous layer at the time. I was mainly thinking about getting some resonance mode in the lateral dimension, because if we have like resonances in this lateral dimension, then we could also utilize the dimension on this side. But when we designed this shape and then checked the absorption coefficient, we saw some absorption peak that was not explainable by just using the resonance mode happening here. So if you see this homogeneous layer sound absorption coefficient, then this is for the 3 centimeter thickness. So the first resonance peak is happening around this frequency. And if we are only explaining this mechanism as the resonance mode happening here, then it is also similar to the thickness, so the sound absorption peak should happen around here as well. But the first absorption peak for this whole Metaporous layer is happening much lower frequencies. And then later we found that this was actually happening because of the slow wave phenomena in the of the sound wave propagating inside this porous layer. So for the acoustic metamaterials with waveguide and also resonators along the side, it was very well known that there is a resonance gap, which has a negative bulk modulus band and a bulk modulus band. But below this resonance gap, there is a frequency range that has slow wave propagation. So the slope of this straight line is the sound velocity in air, and the slope, you can see that slope of this dispersion curve below the resonance gap is lower than the slope of this straight line. And then they have this slow wave propagation in this frequency range. And then how is it related to our Metaporous layer design? So if we take this one unit cell and then analyze the wave propagation behavior inside it, you can see that this is actually very similar to the waveguide and the quarter-wavelength resonators on the side. Then we can also regard it as an effective medium. And then we derive some theoretical model for that. And then this is the final effective density we obtained. So this is effective bulk modulus, and then this is effective sound velocity. And then if you see this graph, you see that this black line is the sound velocity of the original porous medium. And then this blue line is the sound propagation velocity inside this effective medium. And then this is much slower than the sound velocity in the original porous medium. So then we have these horizontal partitions with different lengths. Then we can regard it as a multi-layer of multiple effective layers with different material properties. And we can also calculate effective density and bulk modulus and sound velocity of each medium like this. And then in the end, we define that this has multiple slow waves that has different slow waves in each layer, these effective layers. And back to the sound absorption coefficient of this Metaporous layer. We also conducted full finite element simulation and also effective layer analysis. Then this shows the velocity field inside this unit cell. And then you see that this velocity profile shows the quarter wavelength resonances. And also this velocity profile in this effective layer at this frequency shows a third quarter wavelength resonance mode. Yeah, and by using this slow wave propagation, we could shift down the first quarter wave resonance from 3400 Hertz to 1430 Hertz, which is like effectively 2.4 multiples of the original thickness, and also the second resonance mode from 8500 to somewhere around 2400. And then if we also analyze the wave propagation behavior on these higher peak frequencies, if we specifically look at this third frequency, there is also very interesting phenomena happening. So this one is happening on this frequency, 20 Hertz, and on around this frequency, there is a resonance gap for the last layer happening. So the wave doesn't propagate to this last layer from this frequency on. So there is this second quarter-wavelength resonance mode only from this from 5 layers. Yeah. Yeah, from this only 5 layers. But if we also move to higher frequencies, the this effective medium approach doesn't cannot accommodate all the wave propagation behavior anymore. So in the end, they show more like a confined resonance mode on each quarter wavelength resonators. Yeah, so that was about this my second work, and thankfully there were some researchers who liked my work and then also further expanded my research. For instance, doing machine learning optimization and also using different porous material and expanding some design parameters and also make it as a Sony black hole and so on, and also using 3D printing techniques to generate multiple slow wave at the porous layer. And then after my this second work, I did another work by using slow wave propagation for the sound transmission problem. And then I finished my PhD and started working at the company. And after some years, I came back to academia. But when I was doing my PhD, 3D printing was not 3D printing was available, but the resolution of the 3D printing was not that good at the time. But when I came back, I saw that there are many research using these 3D printing techniques to develop porous sound absorbing porous materials. So these 3D printed porous materials can be also analyzed in a similar way as normal acoustic porous materials. And also there were also research using these 3D printed layers to make a Metaporous layer by using this, including these Helmholtz resonators in the porous layer. And then I found it very interesting. And then as I got the assistant professor position and then had a chance to hire my PhD student, we decided to work on 3D printed sound observers. And my PhD student found this geometry called triply periodic minimal surfaces. This is actually very famous type of geometry that are used in many applications. And this is a class of periodic surfaces with zero mean curvature. And then the shape of this geometry can be expressed very easily by using sine cosine functions. And they are usually known for outstanding mechanical properties. And then very easy to control the geometries by using the mathematical functions. And we decide to utilize this structure to develop sound absorbing materials. But we were not the first ones who thought of that idea. So there were some previous work using TPMS geometry to develop sound observers, but their work was mostly by experimental approach. So they printed this material and then this many measurements to see the sound absorption properties of this. But we wanted to develop some systematic approach to analyze the sound absorbing behavior of the TPMS structures. So we picked one type of cell. I forgot to mention it in the previous slide, but there are many types of TPMS geometries. Among these, we use this primitive type cell, and then the geometry of this cell is expressed by these cosine functions. And then D here means the unit cell size, and then T is the ISO value. So if you change the ISO value T, then you can change the porosity of this unit cell. And then our final goal was to optimize the porosity profile along the thickness of this porous layer to have broadband sound absorption. So to do that, we first started acoustically modeling these TPMS structures. So from the unit cell geometry, we conducted finite element simulation by using constant multiphysics to find the transport parameters that can be used in equivalent fluid medium by using this JCAL model. And then the method to obtain these transport parameters are well explained in this paper. We got a lot of help from this paper, so I wanted to refer this. Sorry. I wanted to mention that this to refer this paper if you are interested in obtaining these parameters from the simulation. So we conducted this simulation for the porosities from 50 to 90% with 5% interval, and for different sizes of the unit cells. And we generate a data set of this porosity and also unit cell size. And then this graph, you can see those transport parameters, viscous permeability, thermal permeability, tortuosity, viscous characteristic length, and the thermal characteristic length. And we found that if we normalize these JCAL parameters to the size of the unit cell, they actually converge to the same values. So we normalize this viscous permeability and the thermal permeability by the square of the unit cell size D, and the viscous characteristic length and thermal characteristic length to the unit cell size D. And then they actually converted to the same value, and then we published a little bit more detail on this aspect on this conference paper. So please check this conference paper if you are interested. And then we can also see that there is a monotonic increase or decrease just for this tortuosity of the parameter values when the porosity increases. So it actually makes the optimization very easier, because if you have like multiple values for like different porosities, then it could be quite fuzzy to get the clean optimization result. And we also did some parameter study by changing some parameter like porosity or unit cell size, and also the thickness of the entire layer. And then we also made this complex plane analysis, which is about obtaining a reflection coefficient in the log scale in the real and imaginary frequency axis. I would not want to go in detail about this complex plane analysis, but there are also poles and zeros of this reflection coefficient if you draw them in this complex frequency plane. And then if the zeros of the reflection coefficient coincide on this real axis of the frequency, then they have full absorption. And then if in case the zeros are located on the above this real axis, then you have underdamping and below is overdamping. So then you get a little bit farther away from the full absorption. And then that can be seen in this sound absorption graph. So for this 70% porosity, this corresponds to this black line. Then you see that on this sound absorption peak, they almost have these full absorptions. But if you are going away from this 70% to 50% porosity, then the sound absorption at these peak frequencies decreases. And then even this 50% porosity, you have quite low absorption values. So similarly, if you move away from 70% to 90%, you also get lower sound absorption coefficient at this absorption peak. Then you can also check these results, similar result, when you increase the unit cell size. For the 1 millimeter unit cell, you have these zeros close to these real axis values. So you have this high absorption coefficient at these peak frequencies. But if you are going away from this unit cell size, then you get lower absorption coefficient. And as we mentioned, our final goal was to obtain the optimal porosity distribution along the thickness. And to do that, we also had to make a multi-layer with each layer has these different effective fluid properties determined by the porosity of each layer. And when you have this each layer, then the sound absorption coefficient of the whole layer can be obtained by this transfer matrix analysis. So we generate a transfer matrix for each of these layer, and then calculate the total transfer matrix. And by using that, we can obtain the surface impedance. And from that, we can get the reflection coefficient and absorption coefficient. And we conducted optimization. So optimization was to minimize the reflection coefficient in the frequency range that we set. And then we also had some constraint on this porosity. And then we used the global optimization toolbox in MATLAB to get the optimal porosity distribution. So this is a result. For the optimization result for the target frequency range from 500 to 6,000 Hertz. So we used unit cell size 1 millimeter, and the total thickness of the sound absorbing layer is 50 millimeter. You see only these 5 unit cells in this figure, but this is not really actual geometry. So we have 50 unit cells along the thickness of this porous layer. So the optimal porosity profile is this red curve. So you see that the optimal profile is actually jumping from high value to low value quite a lot. And we also compared the result when we conduct optimization for the uniform porosity, which means that we have the uniform porosity over this whole thickness, and then that was this value around the 70% porosity. And then we also compare the result with the linearly changing porosity profile from 50% to 90%. And then this is absorption coefficient. So this red line is a graded optimal one, and then these dotted line are for the linear porosity grading, and this black solid line is for the uniform porosity. So you can see that the linear grading can actually improve the sound absorption in between this absorption peak, but not so significantly. But by using this optimal grading, we can actually improve the sound absorption coefficient quite significantly. And these are the values of the average sound absorption coefficient within the target frequency range. But if we go back to this porosity profile, this is quite strange because we usually think that to have broadband sound absorption, it is beneficial to have a structure with like structure with like not changing that much. I mean, like a linear gradation, such as like a wedge form or some curved structure like an egg crate form. But this was quite intriguing, so we decided to do further analysis on that. So to understand that, we first conducted single target frequency optimization. So these are the results. Porosity profiles for the single target frequency 700 Hz and 2000 Hz and 5000 Hz. So what you wanted to do here is to optimize the sound absorption coefficient just below the first sound absorption peak, and also the frequency in between these two absorption peak, and also the one in between the second and third sound absorption peak. So for the first one, 700 Hz, you see that the porosity on the top layers have lower values, and when you get into the bottom side of the porous layer, they have higher porosity at 90%. And for the 2000 Hz, you have this jumping porosity again. And for the last one, 5000 Hz, you get this curve that is somehow similar to sine wave curves. And to understand it better, we also draw this power dissipation density inside the porous layer. So how to read this graph is that pick one line, and then this red color means the power dissipation density at each point inside the porous layer. So for this line, the dissipation is usually happening on the top part of the porous layer, and not really much going on inside this bottom side of the layer. So we could see that to increase the sound absorption coefficient at this 700 Hz, the optimization profile was kind of trying to shift this absorption peak by allocating these layers with lower porosities on the top, which is kind of similar to micropropagated panels. And then also in micropropagated panel. And then if I jump to this third case first, it has this gradually changing sound wave like a profile. And then you see that when they have these lower porosities, they have slightly increased dissipation. And then by modulating this porosity, they also change the tortuosity inside the whole porous layer. So they can actually shift this peak to the lower frequency. And also this one in the middle, this one was a little bit extreme case because we were trying to improve the sound absorption coefficient, which was in the quite low value to a higher one. So the optimization produced this very jumping profile to move this peak frequency and also increase the dissipation. Yeah, so we thought that and it helped a little bit on understanding how we obtained this very jumping porosity profile. So the optimization was in the end trying to shift this absorption peak and also increase the dissipation inside the layer. So it generates these low porosity values to change the tortuosity inside the layer and also improve the dissipation at certain locations. And then we also did experimental validation of this work. So we 3D printed these samples by using digital light processing, by using this 3D printer. The resolution of the 3D printer that we used was 33 micrometer. We used 1 millimeter unit cell for our simulation, but it wasn't really possible to print the samples with 1 millimeter unit cell. So instead, we used 3 millimeter unit cell. And then we conducted a measurement by using this impedance tube. And we did a measurement for different type of porosity profile, one with just single porosity, and the one linearly gliding, and also one with a little bit of jumping type of porosity, and also the optimized one for this 50 millimeter layer, and also this sine wave type of porosity profile. And then the one in the bottom shows absorption coefficient. These dotted lines are from our theoretical model, and these red lines are from the measurement. And then you can see that the theoretical model and the measurement result match quite well, but there are also increase of the sound absorption coefficient in the measurement ones, because when we actually print those samples, they cannot really replicate the size and the geometry very precisely, so they have a little bit of increase on the dissipation when we actually print those samples. So that was all from my side today. So to conclude, I showed these 3 works about engineering porous materials to get a broadband sound absorption. So for the Metaporous layer, I show the approach in including some rigid partitions to modulate the wave propagation length and also sound wave velocity inside the homogeneous porous layer. And for this 3D printed lattice structure, I show the approach to find optimal gliding profile along the thickness of the sound absorber. And future work might include combining these 2 methods. I see that there are already some works trying to combining this Metaporous layer approach and also 3D printed lattice structure. And the other work could also include trying different unit cell geometry and also overcoming the manufacturing challenges. Yeah, thank you very much for your attention. And then I have my email address here. So if you have any questions, please feel free to send me an email. And if you have any question, I would happy to answer right now.
Thank you, Ji-yeon. That was great. Thank you very much. Does anybody have any questions? There is a Q&A button at the bottom. You can ask any questions. I think Keith has got a question. If you put it in the Q&A, we'll be able to have a look and answer that for you. Keith, do you want to ask your question?
Oh, thank you. Yes, I don't type very quickly. Sorry.
That's all right.
So this is very, very interesting presentation. Very, very nice work, which of course I've used a lot in a couple of my publications. Certainly the work on partitions. I hope you've seen my papers too.
Thanks a lot.
So classically, one looks at flow resistivity rather than porosity. Have you calculated flow resistivity, and can you do better than impedance matching in your optimization for the graded structures?
For the flow resistivity, the model that we use is JCAL. So yeah, and for this model, we don't calculate the flow resistivity, but something related to the flow resistivity. I forgot which one it was. Probably that does thermal permeability, and then that is directly related to the flow resistivity of the porous layers, if I remember correctly. Yeah. And your second question was about impedance matching. So if we could do better than impedance matching, I'm not so sure about that. So for the physics of this porous layer sound absorption, in the end, we should match the impedance between this air and this porous layer to get full absorption. And if we want to do more than impedance matching, that means that we probably need to break the physics law. Yeah, and then I'm not sure if it is possible to do that in the end. Did I answer your questions correctly?
If I'm still unmuted, yes, that's fine. I think, though, some of the conclusions you reached could have been reached more easily if you looked at flow resistivity, since classically we know that for a given layer thickness, the lower the flow resistivity, the more resonant will be the absorption coefficient in terms of frequency. And so that explains a lot of why you're getting more resonant. Well, it could explain why you're getting a more resonant absorption spectrum for your low porosity cases.
Yeah, that is a good suggestion. We will look into that again. Yeah, these parameters are somewhat related to the flow resistivity for sure. But we didn't really look into the flow resistive value. Oh, yeah,
I think it would be interesting. Yeah, I think it would be interesting because it combines both it actually depends on at least two of those parameters,
Yeah,
the viscous
yeah.
permeability and the tortuosity, and also the porosity. So that is why classically flow resistivity has been used a lot in describing the absorption properties of porous materials.
Yeah, indeed. Yeah. Yeah, we will check that later. Yeah, thanks for the good suggestion.
Great, thank you. Claire had a question. I'll just switch over to Claire. Claire, did you want to ask a question? No. Are there any other questions before we finish this morning? Either in the chat or raise your hand. No? Okay, I think that's it. So thank you, everyone. Thank you, Jae-yoon. Thank you for this morning. The recording will be available on YouTube on the UKAN website.
Yeah, thanks a lot, everyone, for joining this session. And if you have any questions that you couldn't ask today, please send me an email. Yeah, here.
Great, thank you. Thanks, everyone.
Thank you very much. Bye-bye.
Bye-bye.